Hello, and welcome to the CIBSE Journal CPD Module 263, Transcritical CO₂ Heat Pumps for Commercial Buildings. This module explores why transcritical carbon dioxide refrigerant heat pumps have emerged as low GWP options in commercial heating and domestic hot water appliances. This module is sponsored by Clade. Decarbonising heat in commercial buildings has become one of the central challenges for the built environment. Heating and domestic hot water, or DHW, remain major contributors to operational carbon emissions, particularly across large public sector estates, hospitality, healthcare and education facilities that rely on fossil fuel boilers. The UK's legally binding commitment to achieve net zero greenhouse gas emissions by 2050 is accelerating the transition away from gas-based heating systems. Electrification of heat is widely recognised as a primary pathway to achieving this transition, particularly as the UK electricity grid continues to decarbonise through increasing renewable generation. Heat pumps play a central role in this shift. However, conventional heat pumps using hydrofluorocarbon or HFC refrigerants can face limitations in commercial retrofit applications. Many existing buildings operate heating systems designed around high water temperatures, often exceeding 60 degrees C. These temperatures are typically required for legacy radiator systems or for large domestic hot water demands in buildings such as hotels, hospitals, and leisure centres. Conventional heat pumps may struggle to achieve these temperatures efficiently without system redesign. At the same time, regulatory pressure is reshaping refrigerant selection. European and UK F-gas regulations are progressively phasing down high global warming potential, or GWP, refrigerants, reducing the availability of many synthetic HFCs. This has increased industry interest in natural refrigerants that can offer both lower environmental impact and long-term regulatory certainty. Carbon dioxide, or CO₂, also known as refrigerant R744 or 744, has emerged as a promising option. CO₂ has a GWP of 1 and 0 ozone depleting or ODP potential and is classified as an A1 refrigerant, meaning it is non-flammable and of low toxicity. CO₂ heat pumps typically operate using a transcritical cycle, which differs fundamentally from a conventional vapor compression cycle system. This cycle allows the production of high-temperature water, often more effectively than conventional systems in uses with large temperature lifts, making the technology particularly attractive for commercial heating and domestic hot water service applications. Thermophysical properties of CO₂. The behavior of a refrigerant within a vapor compression system is governed by the thermophysical properties. CO₂ differs significantly from conventional synthetic refrigerants, and these differences strongly influence system design and operation. Figure 1 is a phase diagram for CO₂ at temperatures from -80 degrees C to 80 degrees C. The diagram is divided into regions representing solid, liquid, gas, and supercritical states, separated by phase boundaries where transitions occur. Overall, the diagram illustrates that the state of CO₂ depends on both temperature and pressure, and highlights the absence of a liquid phase at low pressures and the emergence of supercritical behavior at higher temperatures and pressures. One of the most important characteristics of CO₂ is its low critical temperature of approximately 31 degrees C, combined with a critical pressure of about 73.8 bar. In many heat pump applications, the temperature at which heat must be rejected exceeds this critical temperature. When this occurs, the refrigerant cannot condense regardless of pressure. Instead of operating as a conventional subcritical cycle with condensation, the system operates in a transcritical cycle. The critical point is the highest temperature and pressure at which a pure material can exist in vapor-liquid equilibrium. In transcritical operation, the high-pressure heat rejection process occurs above the critical point. Rather than condensing, the refrigerant passes through a gas cooler, where it remains in a supercritical state and cools sensibly. During this process, the refrigerant temperature decreases continuously rather than remaining constant as it would during condensation. This produces a temperature glide along the heat exchanger. The glide allows the refrigerant temperature profile to more closely match the temperature rise of the water being heated, reducing temperature differences and improving heat transfer effectiveness. Several additional thermophysical characteristics reinforce these advantages. CO2 has a high vapor density and volumetric heating capacity. This enables the same heating capacity to be achieved with smaller compressors and significantly reduced pipe diameters, which could be advantageous in plant rooms where space is constrained. The refrigerant also exhibits low viscosity and high thermal conductivity, resulting in high heat transfer coefficients and allowing heat exchangers to be relatively compact. Other important characteristics is the triple point of CO2, occurring at approximately minus 56.6 degrees C and 5.2 bar. If pressures falls below this level, CO2 can solidify into dry ice. System safety design must therefore ensure that pressure relief and venting arrangements prevent conditions that could allow solid CO2 to form and block discharge paths, particularly during rapid depressurization or maintenance conditions. While these properties create engineering challenges, they also enable a distinctive heat rejection process that is well suited to high temperature heating applications. Thermodynamic operation of the transcritical CO2 cycle. The key feature that distinguishes CO2 heat pumps from conventional systems is the transcritical vapor compression cycle. While the basic components remain similar to other heat pump technologies, compressor, heat rejection, heat exchanger, expansion valve, and evaporator, the behavior of the refrigerant differs because the high pressure side of the system operates above the critical point. The thermodynamic cycle is typically illustrated on a pressure enthalpy pH diagram. See Figure 2. In a transcritical CO2 system, the high-pressure section of the cycle lies entirely above the saturation dome, reflecting the fact that the refrigerant does not condense against during heat rejection. Although the overall cycle resembles a conventional vapor compression system, several important differences influence how CO2 heat pumps operate and how their performance should be assessed. Compression. The cycle begins with low pressure vapor leaving the evaporator and entering the compressor at point 1. The compressor raises both the pressure and the temperature of the refrigerant. In typical commercial systems, the pressure increases from around 20 to 45 bar at the evaporator outlet to approximately 80 to 120 bar at the compressor discharge. During compression, the refrigerant passes through the critical point and enters the supercritical region. Above this point, the refrigerant no longer exists as a distinct liquid or vapor phase, but behaves as a dense fluid with properties of both. One practical implication is the high discharge temperature produced by the compressor, often exceeding 100 degrees C, this being system dependent and can be lower with optimization. This enables the heat pump to deliver high temperature water suitable for space heating or domestic hot water applications. Gas cooling. After compression, the heat pressure refrigerant enters the gas cooler, where heat is rejected to the building heating system. In conventional refrigerant heat pumps, heat rejection occurs through condensation at a constant temperature. However, because the CO2 is above its critical temperature, it cannot condense. Instead, it cools while remaining in a single supercritical phase. As the refrigerant flows through the gas cooler, its temperature decreases continuously. This produces a temperature glide along the heat exchanger rather than the constant temperature profile associated with condensation. For building services engineers, this behavior is important because it allows the refrigerant temperature to follow the temperature rise of the water being heated. The result is often a closer match between the two fluids, which reduces temperature differences within the heat exchanger and improves heat transfer effectiveness. This characteristic is one reason why CO2 heat pumps can effectively produce high outlet water temperatures, particularly when heating cold water streams, such as domestic hot water services supplies. Expansion. After leaving the gas cooler, the refrigerant passes through an expansion valve, The valve reduces the pressure of the refrigerant from the high gas cooler pressure to the much lower evaporating pressure. This throttling process occurs without any useful work being recovered, making it inherently irreversible. As pressure falls rapidly, the refrigerant temperature also drops and part of the fluid flashes into vapor. The mixture leaving the valve therefore consists of both liquid and vapor. In CO2 systems, the pressure difference across the valve is particularly large, so a relatively high proportion of flash gas is produced. Flash gas refers to vapor that forms immediately during the expansion rather than within the evaporator, which reduces the useful evaporator heat uptake cycle efficiency of the system. For this reason, the expansion process represents one of the largest sources of thermodynamic loss within the transcritical cycle. Evaporation. The low-pressure refrigerant mixture then enters the evaporator, where it absorbs heat from the source medium. Depending on the system configuration, this source may be ambient air, water, ground loops, or waste heat streams. As heat is absorbed, the remaining liquid refrigerant evaporates. Unlike the gas cooler process, the evaporator operates below the critical pressure, so the refrigerant behaves like a conventional boiling refrigerant. The mixture gradually becomes saturated vapor and is typically slightly superheated before returning to the compressor at point 1. Architecture and key components. The transcritical cycle leads to a system architecture that differs from conventional HFC heat pumps. While the main components are similar, they must be designed for higher pressures and specific control requirements. The compressor draws low-pressure vapor from the evaporator and compresses it to the high pressures required for transcritical operation. Reciprocating compressors are commonly used in commercial CO2 systems because they can reliably handle large pressure differentials and dense refrigerant. High-pressure scroll compressors are increasingly used in smaller systems. Variable speed drives are frequently incorporated to match heating output to building demand and improve part load efficiency. In place of a condenser, transcritical systems use a gas cooler to reject heat to the heating circuit. Gas coolers may be air-cooled, finned heat exchangers, or water-cooled plate heat exchangers. In many commercial systems, the gas cooler is optimized for domestic hot water production, allowing cold mains water to be heated from around 10 degrees C to 60 to 70 degrees C in a single pass. CO2 systems typically use electronic expansion valves rather than thermostatic valves. These regulate refrigerant flow while also controlling the high side pressure requirement for optimal system performance. Rapid electronic control allows the system to adapt continuously to changing operating conditions. Because of the high operating pressures involved, pipework and components must be constructed from pressure-rated materials and installed using specialized jointing techniques. However, the high-pressure elements are generally contained within the monoblock unit, which will have been manufactured to the Pressure Equipment Directive regulations. Performance characteristics. The coefficient of performance, or COP, of a CO2 heat pump depends strongly on the system design and operating conditions. A key difference between transcritical and conventional heat pump cycles is that the high side pressure is not fixed by a condensing temperature. In a subcritical heat pump, the condensing pressure is directly related to the temperature at which condensation occurs. In contrast, the gas cooler pressure in a transcritical CO2 system can vary independently of temperature. For any given operating condition, there is, therefore, an optimum gas cooler pressure that maximizes the heating capacity while minimizing compressor power. Modern CO2 heat pumps continuously adjust this pressure using electronic expansion valves and control algorithms. By optimizing high side pressure in response to changing heat source and heat sink conditions, the system can maintain the best possible coefficient of performance. Return water temperature. The efficiency of the cycle is strongly influenced by the temperature of the water entering the gas cooler. Because the refrigerant rejects heat sensibly rather than condensing, the ability to cool the refrigerant within the gas cooler strongly affects efficiency. Increasing the inlet water temperature to the gas cooler has been shown to reduce COP by up to around 6% in experimental studies of transcritical CO₂ heat pumps. If the return water temperature is low, the refrigerant can be cooled more effectively before it reaches the expansion valve. This increases the useful heating capacity of the cycle and improves overall efficiency. Conversely, if return temperatures are high, the refrigerant cannot be cooled sufficiently in the gas cooler. This reduces the available enthalpy difference across the heat exchanger and increases losses during expansion. For this reason, CO₂ heat pumps perform particularly well in applications where cold water is heated through a large temperature lift, such as DHW production. These characteristics explain why CO₂ heat pumps perform especially well in DHW applications. Heating cold mains water from approximately 10 degrees C provides ideal conditions for cooling the refrigerant in the gas cooler, enabling efficient operation even when delivering water temperatures above 70 degrees C. Conversely, systems connected to legacy heating circuits with high return temperatures may experience reduced efficiency because the refrigerant cannot be sufficiently cooled before expansion. CO₂ heat pumps can be used for space heating in new builds, where a return temperature of 30 degrees C is possible using small diameter pipes. Low pumping demands make this efficient in operation, but designing, installing and commissioning such a system will require specialist technical input. Ambient conditions also affect performance. At low outdoor temperatures, air source systems may experience reduced capacity and require periodic defrost cycles. High ambient temperatures can also reduce efficiency because heat rejection becomes more difficult. Part load performance is another important consideration. When heating demand falls below the minimum heat pump capacity, frequent start-stop cycling can reduce efficiency and increase compressor wear. To mitigate this, systems commonly incorporate variable speed compressors and thermal buffer storage. With appropriate design and control strategies, commercial CO₂ heat pumps can achieve seasonal COP values in the range of 2.5 to 3.5, with higher values achievable in optimized DHW applications, where the COP can exceed 3.5. Applications in commercial buildings. The thermodynamic characteristics of transcritical CO₂ heat pumps make them particularly well suited to applications requiring high temperature hot water. DHW production is one of the most common uses. Buildings such as hotels, hospitals and leisure centres often require continuous hot water supply at temperatures suitable for thermal hygiene and Legionella control. CO₂ heat pumps can produce water temperatures typically 60 to 80 degrees C, with higher temperatures achievable in specific applications, without supplementary electric heating, making them well suited to these uses. Designers should note that where secondary circulation systems are included, these may need a small electric heater and/or a preheat tank to account for standing losses. Another emerging application is waste-to-heat recovery, particularly in data centers. CO₂ heat pumps can simultaneously provide cooling for IT equipment while upgrading rejected heat to useful hot water temperatures for building heating or district heating systems. Emerging developments. Recent technological developments aim to improve the efficiency and operating range of transcritical CO₂ systems. Parallel compression is one approach that separates flash gas generated during expansion and compresses it using a dedicated compressor stage. This avoids unnecessary recompression through the main compressor and can improve system efficiency. Another innovation is ejector technology, which recovers some of the expansion energy normally lost during throttling. By entraining low-pressure vapor and particularly compressing it, ejectors reduce compressor workload and improve cycle efficiency. Future developments could also include integrated systems capable of simultaneously providing heating, cooling, and heat recovery. Combined with advanced digital control systems that optimize gas cooler pressure in real time, these developments are improving system seasonal efficiencies and expanding the range of suitable applications. Growing regulatory pressure to reduce carbon emissions and phase down high GWP refrigerants is accelerating the adoption of alternative heating technologies in commercial buildings. Transcritical CO₂ heat pumps offer a low GWP solution capable of delivering high temperature heat while supporting the electrification of building heating systems. With the building services industry undergoing a paradigm shift as it strives to improve the energy efficiency of new and existing buildings and make them inherently safer, members of CIBSE need to focus their learning and development on key industry issues. Members of CIBSE and other professional bodies are required to maintain their professional competence throughout their careers. Please visit the link in the description should you wish to obtain a certificate to keep on your CPD record.